So we're going to piggyback on what we were talking about on Monday about Q is equal to MC sub P delta T. But in the meantime, there are many things in this universe that have to be conserved, and energy and matter are right at the top of them. So the conservation of energy is one of the things we're going to count on when we do thermodynamic problems. So the energy can be transferred, and in ours, maybe you guys know that Einstein says you can convert energy to matter and matter back to energy, or energy, yeah. But we aren't going to be doing any of that, okay? So in order to work thermodynamic problems, it's just the study of the flow of heat. And there are some common names or some common terminologies. And to me, it just screams a picture. A lot of times, this is going to be kind of the case tomorrow. Tomorrow we're doing a calorimetry experiment. Not colorimetry, calorimetry, counting calories, counting energies. And it's actually, you're going to come up with the specific heat for copper. So I'm not sure what number that is, but that's what you'll be doing. This is my proverbial beaker, and I put a liquid in my beaker. Oftentimes, actually, this is our system of interest. Okay, so the system is the thing that you're looking at. I'll go ahead, in tomorrow's lab, I'm going to go ahead and throw in, this is supposed to be a block of metal. Okay, so my system is basically contained by my beaker. So this is the system. Anything outside the system would be your surroundings. Okay, so these are my surroundings. Sometimes surroundings is called the environment, the stuff outside the system. And of course, the boundary is the thing that separates the system from the surroundings. So in this case, the boundary would be like the glass that's containing our liquid that also has a chunk of metal in there. So we oftentimes count on our system being insulated. Now, I know the word insulated isn't up here, but if you think of a container that's insulated, why do you insulate that? You try to keep the heat from going in, or if it's hot coffee, the heat from going out, okay? So an isolated system is one that basically there's two things. There's no energy transfer outside from the system out to the environment or out to the surroundings, nor is there any, there's no energy or mass transferred. Mass is pretty easy because you're like, dude, just don't spill it, right? Energy is a subtle thing, though, because energy likes to kind of work through glass and styrofoam. So the term isolated and closed for purposes of this course, we're going to use them synonymously, isolated system, a closed system. But oftentimes, they're actually distinguished between what's being contained. So for instance, a closed system is containing mass. An isolated system is containing energy. So, but I use them interchangeably. So let's work another Q is equal to MC sub P delta T problem. Now I'm going to go ahead and this kind of takes on a classic form. I'm going to draw a picture. And it's going to look just kind of like the picture I drew a minute ago, where I'm going to make my system in a beaker. Okay, I'll make my water blue. And so we have water, and then if you read the problem a few times, we also have aluminum. So I'll go ahead and make this is my kind of block of aluminum. But tomorrow you guys are going to be working with aluminum shot. So I have aluminum, and I have water. And we're going to we're going to assume that basically there's no matter transferred outside of the beaker, nor is there any thermal energy transferred outside of the beaker. So I'm going to show you what I do, and then you'll kind of catch on why I do this as we work problems. I'm going to go ahead and make all my things about aluminum on the left, and I'm going to make all my things about the water on the right, and I'll show you why. So it says, and let's go ahead and just do this. Let's remember Q, change in thermal energy of anything, is equal to the mass of that thing times the specific heat of that thing times the change in temperature that thing undergoes. Q is equal to MC sub P delta T. Okay. So now let's look and kind of see what we got. So let's go ahead and just do it this way. I'll write those variables. Q, oops, that's a G. Q, M, C sub P I'll put, remember delta T is T, final minus initial, TF minus TI. So I'm going to put TF, I'm going to put TI for both of these. We got time. Q, M, C sub P, TF, TI. How's that? All right, I think we've stalled long enough. So, and no mass of aluminum. So under my mass of aluminum, I'm going to put question mark. Right? Notice it gives the specific heat of aluminum as 0.902 joules per gram degrees Celsius. Cool. It says that aluminum is heated 98.7 degrees Celsius, and then it is submerged into the water. So do you buy, would this be, would the 98.7 degrees, I'll tell you, it's your initial temperature. So I'm going to find my T sub I, and I'm going to say 90. I was going to ask it in the form of a question, but so far so good. And it says that hot aluminum is immersed into 50 grams of water. So now I have the mass of the water equals 50.0 grams. Don't put it as 50 grams because that's a different number than 50.0 grams. It says the initial temperature of the water, so I find my T sub I, is 22.0 degrees Celsius. Now, you probably buy this that if you, and this is what's going to happen to your lab, in your lab tomorrow. Basically, you're going to take the hot aluminum and put it into the cooler water, and your aluminum's going to cool down and your water's going to warm up. And they're going to warm up to a common temperature. That's the equilibrium temperature. So when it says the equilibrium temperature was 33.3, that's actually going to be the final temperature of my water, and that is also going to be the final temperature of my aluminum.
The initial temperature for the one is 22.2. Does it matter that much that you put 22.2?
Oh, thank you. Yeah. Yeah. Rhonda's saying, making sure that I should correct this. Thank you. 22.2. Good catch. Okay, so this is kind of what we got. Now, do you guys know the specific heat of water? Yep. Almost. Joules per gram degrees Celsius. Yep. Very good. This kind of reminds me of our titration problems. Do you see where we pretty much know everything about the water to get Q? And we're going to use that to our benefit. Okay? And then I'm going to show you how, Q of the water is related to Q of aluminum. And once we have Q of aluminum, which we can get, can you see then actually we're pretty close? Because then all we need is the mass of the aluminum. So in order to kind of finish this, but this is actually, as I show it up here, if I have the time, which usually I do if I'm working problems, whether it's for whatever reason, I just draw a picture like this, and it just, because there's too many numbers. All right. So an isolated system is one in which neither mass nor energy is transferred past the boundary from the system to the surroundings. So as we are conducting this little problem, our system of interest, the stuff of interest, is what's contained in the beaker. It's the water and then the aluminum once it's added. Okay? And we're assuming, like I said, and that's kind of a stretch, because you know if you put your hand against that glass, it's going to heat up, but we're assuming it's isolated. So intuitively, I'm sure you guys would all agree that you put something hot like aluminum into your cooler water, your water's going to warm up, and your aluminum's going to cool down to that equilibrium temperature. So in other words, the energy that heats up the water was the energy that was lost by the aluminum. And, right? Yeah. Put another way, anything the aluminum has to give off is going to be accepted by the water. And I'll go ahead while you guys are filling in blanks. I'll write my little beaker. I just think that is so cool. Here's my beaker. Here's my water. You know, here's my aluminum. You know, and the aluminum was hot, and it cooled down, and the water was cooler, and it warmed up. I just think that's so cool. You can't really, you can visualize the energy exchange, but you don't really see it. You put a thermometer, and you can see something's happening. Energy's an awesome thing. Okay, so our system is our beaker, and our beaker contains the water, which is heating up, and the aluminum, which is cooling down. We said that it's isolated, so the change in thermal energy of our system, 0. Okay, but within our system, we have 2 objects, aluminum and water, and they are changing thermal energy. Specifically, the aluminum's giving it up, and the water's taking it in. So the change in thermal energy of our system, it's kind of, I couldn't remember why I thought of what happens in Vegas stays in Vegas. I don't know. Win a lot of money, lose a lot of money. So it's, some exchanges are occurring, but they stay there, okay? So we know we can actually, I don't remember which property of math it is, but we can now say that the change in thermal, since the Q of the system is 0, and the Q of the system is the Q of aluminum plus the Q of water. Right, thank you, substitution. Therefore, the Q of aluminum, change in thermal energy of aluminum plus the change in thermal energy of the water is equal to 0. And we know we can rearrange that thing, and you get this. So in this case, Q of the aluminum, change in thermal energy of the aluminum, is equal to negative change in thermal energy of the water. I wanted to make sure I warned you guys, because sometimes working these problems, we don't put Q of system is equal to the change in thermal energy of the system. We have 2 things in there, the aluminum and the water, Q of water, Q of aluminum. Sometimes we don't put that down and it gets lost in translation. Sometimes there are actually 3 terms. Sometimes there's 4 terms within your system. So what's going on with regard to energy changes? In this case, there's just 2. So don't just automatically set one equal to the negative of the other. Okay, so here we go. All right. So remember back, we had the beaker and we had kind of all the stuff about aluminum over on the left, all the stuff about the water on the right, okay? This is actually all the stuff about the water. This is all the stuff about the water that I wrote a minute ago. And I kind of told you it's like a solution concentration stoichiometry titration problem. It's like a titration problem. What do you know the most about? We know the most about the water. Can we get to the Q of the water? Yes, we can. The mass of the water is 50.0 grams. The specific heat of water, you told me, 4.184. That's joules per gram degree Celsius. I know it's kind of written weird like that. And then delta T is always final minus initial. So in this case, it's that equilibrium temperature of 33.3 degrees Celsius, and we're subtracting 22.2 degrees Celsius is the initial temperature of the water. This actually introduces something that you'll see in my answer keys, and that's totally acceptable. I'm all about units, I really am, okay? But if you're adding or subtracting numbers that have the same units, it's fair game to go ahead and put those numbers in parentheses, and then outside the parentheses put the units, okay? So anyway, so here we go to get the Q of the water. Now, working these problems, it's important to stay organized. And oftentimes, it's important to go ahead and write subscripts. So we have actually 3 Qs. We have Q of system, Q of water, Q of aluminum. Okay, so if I'm grading your paper and I can't follow what, even if you get the right answer, I'm going to, for these problems, I might be more picky than I have been before. You have to communicate to me what Q you're talking about. So this is the Q of the water. Q of the water is equal to the mass of the water, 50.0 grams. Times the specific heat, 4.184. That would be joules in the numerator, gram degrees Celsius in the denominator. And the delta T we decided, rounded to the correct number of decimals, is 11.1 degrees Celsius. I put it over 1. So now we go ahead and let units cancel, the fun part of working problems. So grams cancel, degrees Celsius cancel, we're left with units of joules, which is perfect. Okay. So rounding it to 3 significant figures, and you guys know you don't have to, this isn't scientific notation. You don't have to pack it up in scientific notation. You could have put, what, 2,320 joules, same diff. Okay? And I think we talked on Monday, sometimes, for whatever reason, we want joules all the way into kilojoules, which we could do, but we're not going to do right now, I don't think. Okay? So that's Q of water. Now, you go back a few slides, we said Q of aluminum is equal to negative Q of water. Okay? Now, if you have that in your stuff that you're working, you are ready to go ahead and just step up and say Q of the aluminum is equal to negative 2,320 joules. But you can't do this step unless earlier you showed how you got to this step. Okay? Does that make sense? And on Monday, one of the things I want to keep, if you can, keep in the back of your mind, we talked about positive Qs and negative Qs, okay? And we said positive Qs were things that were accepting energy, and the water was positive. And negative Qs are things that are giving up energy, and that's negative. So it's consistent, okay? That would be, what, endo and exothermic respectively. All right. So then we switch gears to the left half of my figure, and then we look to the aluminum. And what do we know about the aluminum? Well, we know its specific heat, and we know it's delta T, and now we know it's Q. So you can rearrange Q is equal to M C sub P delta T, and to get, and if you're like me, you have to be really careful because it's easy to butcher this with the algebra. So if I want mass, I'm going to divide both sides by C sub P delta T. Okay, and that's what I got here. So don't butcher it. Okay, it's really easy to make a mistake. But here I am going to rearrange and plug in. So here we go. Oh, yeah. Okay, so what's all the stuff now about the aluminum, not the water, the aluminum? Well, we got to Q of the aluminum is, and I probably, and my answer key would put a little subscript AL there. Q of the aluminum, we decided, was negative 2,320 joules. Specific heat was given, 0.902 joules per gram degree Celsius. Our delta T is final minus initial, so it's that equilibrium temperature, 33.3, minus the initial, which was the hot, 98.7. Rounding according to decimals, that gives us a delta T, and don't forget that negative is important, okay? Negative 65.4 degrees Celsius. Now we're ready to plug these values into our equation, keeping our units, and it looks like this. So M, or mass of aluminum, and sometimes when I'm working these, I don't have it here, but I give everything little subscripts because it just gives me comfort. Mass M of what? Well, we're working with the aluminum. Mass of aluminum is Q negative 2,320 joules divided by specific heat, 0.902 joules per gram degree Celsius. Also in the denominator is the delta T, negative 65.4 degrees Celsius. So let's see what cancels. Let's see. We got, yep, Celsius canceling. Yep. Joshua says joules canceling. Now this happens sometimes. Notice that we basically have grams in the denominator of the denominator. Now you're going to have to find a mathematician to explain this. But bottom line, if it's in the denominator of the denominator to resolve it, it actually is in the numerator. So that is units of grams.
Just because you're just taking the reciprocal.
Yeah, you're dividing by, yeah.
You divide it by, you just take the reciprocal.
Okay. Okay, so that's grams. All right, so round to 3 significant figures. And the mass of that hot aluminum must have been 39.4 grams in order to impart that change on that particular volume of water. I just think that is so cool. No pun intended. Okay? So again, kind of on my slides, it's kind of missing a little bit, you know, of maybe some of my subscripts that I would try to make sure. And it could be that if I was working this and I had my little figure of a beaker, this stuff would be over here on the left with all my aluminum, and it'd be kind of organized that way. So, cool. All right, so 1 and 2 are due today, but we got 4, 5, 6, and 9 lined up for due on Friday. Fabulous Friday. So we'll take a quick look at those. And they look like this. So I can't remember, I think I drew some pictures. Yep, here's some pictures, right? So if you don't want to read the words, you can actually just look at my pictures and see what the words say. So instead of aluminum, we have silver. Okay, what do we know about the silver? It's kind of given over here. What do we know about the water? Again, we're going to douse it in water, kind of like what you guys are going to do tomorrow. Okay, the initial temperatures are given. And notice we have, again, the common final equilibrium temperature. So T sub F, now that won't always be the case, but for these two problems it is. Okay, so the aluminum cools down to this temperature and the water heats up to this temperature. This is very similar, but instead of going for the mass, we're going to go for the specific heat of silver. And this is actually very much what you guys are going to do tomorrow. That's specific heat for copper. So just to kind of remind you what we talked about, I really probably should see that the change in thermal energy of the system, it's isolated, it's equal to 0, and we have two things changing energy. We have the silver changing energy and the water changing energy. And then you can rearrange that to say one is the negative of the other. Okay, start over there with your water to get your Q of your water. You can do that. And then apply the one is the negative of the other. Again, it's not always just 2 terms in your system. Sometimes there's a third or even a 4th term. Okay, so I think you should be okay there. The next one looks like this. Let's look at the picture I drew. We have iron being added to water. The mass of the iron is given, the mass of the water, the specific heat of water, of course you memorize. The temperature of the water, the final temperature of the water is also given. The specific heat of the iron. Oh yeah, this is one where you're supposed to find out how hot was that iron, okay, as it was added to the water. So again, where do you start? Well, you're going to start with your water. But I would somewhere in there identify your system, change thermal energy of your system is equal to 0, and it's equal to the change in thermal energy of the iron and the water. Your iron's going to cool down, your water's going to heat up. And then you can set one equal to the negative of the other. So again, I would start over here, get Q of that, Q of water. Then, of course, that's negative Q, that's negative Q of that. Okay? And then what I would do is just rearrange Q is equal to MC sub P delta T, solving for delta T. I would leave it bundled as delta T. Okay, that's what I would do. And then once you have delta T for the iron, then I would recognize that delta T, I would expand it. Delta T is the final, which you know, minus the initial, which you don't know. Okay, so that's what I would do. But that's just me. Whatever you do, you have to communicate it. Let's see what this picture is. Oh, there's my stainless steel ball. Must have been thinking about that kind of crunchy sort of thing. We don't know the mass of the stainless steel. We know specific heat, initial, final temperatures. Now in this case, the water, it's a similar scenario. But you're not given the mass of the water, but you're given the volume and you know the density of water. And you're supposed to memorize the specific heat of water. So it's very similar to kind of what we've been doing, very similar. What is the mass of the steel? And then last but not least, we have this one. Well, there's my little copper shot. That's like, wow. So we have the mass of the copper, specific heat of copper, the initial final temperature of the copper. We're going to put it not in water, we're going to put it in glycerol. Again, you're not given the mass of the glycerol, but you're given enough information to find it. So you're going to have to knock out the mass of the glycerol. Oh, yeah. Oh, now look at this case. Well, you're not given the specific heat of the glycerol. So this time you have to start over here. You have enough information over here to come up with the thermal energy change in the copper. And then you're going to set the change in thermal energy of the glycol is negative change in thermal energy of the copper, just because in these, all three of these, there's only two things going on. Okay, so this is a good, homework is good, so you guys can do it, and I can take a look at it and make sure you get all the points on the test, quite frankly. Okay, all right. On to the next part. So I'll push these out there. What's that?
What is it?
Glycerol, it sounds dangerous. Glycerin, glycerol, maybe. What I'm thinking of is kind of a liquidy. I think we've used it on like as a lubricant, so it's just like a that you have around the lab.
Hair products in that too.
It's in hair products.
Not cares for it.
Maybe it's like a moisture thing. It's
Moisture.
yeah, it keeps its. It doesn't dehydrate. That's what I'm thinking of. That's not you guys. This is you guys. It's messed up camera. Okay. So on to part 3. Part 3 has 14 slides. Again, if you're a slide counter, this is coming. Okay. So I feel like we've talked about endo and exothermic, the terms before. Okay, and we're going to revisit that. Endothermic and exothermic, the concepts are important in thermodynamics, the study of where did that heat go, where did it come from. So if something is an endothermic, and I think I probably said this before when we've run into this, I think endo, I think in. And we've been talking about a system. So basically an endothermic process is where the system takes in the energy. And we said actually, we said that the change in thermal energy of the system for something that's endothermic would be positive. Positive, i.e. greater than 0. Now the process could be a lot of different things. It doesn't have to be a chemical reaction. In this case, the process is actually a phase change. So in order to melt ice cubes, or in order to melt anything that's solid to go to its liquid stage, you need to add energy. Okay, that's an endothermic process. And we'll be talking about that little energy later, this latent heat. Then exothermic, exit, leave, exit. So that's actually a situation where the system is giving up, energy to the surroundings. So I was kind of pause, what is that? I guess to the surroundings. It's not being given up to something within the system. So exothermic, and we said that that is negative actually. Exothermic processes will have a negative Q, change in thermal energy. All right, and here's an example of something that's exothermic. It just looks exothermic, doesn't it? Looks hot. Okay, it's like heat is being released. In that case, actually, system's not isolated, is it? If the system is our beaker, okay, it's not isolated with regard to energy nor mass. You see that stuff blowing out of there, okay? Okay. System of interest, the thing you're looking at or focusing on, okay? So there's actually the overall internal energy of the system. Now that doesn't have to be thermal energy, it's just energy. Could be partly thermal energy. So we talked about, you see the, I almost said diamond, you see the triangle, Okay, that means that's the Greek letter delta, that's change in. So change in energy of the system can be thought of as actually kind of two terms. Change in thermal energy of the system, and any work that's done by the system or on the system. The W term is work. A lot of times in chemistry, we just ignore that. I think in physics, you worry about it more than we do, okay? Okay, so this is the first law of thermodynamics. Change in internal energy of the system is equal to change in thermal energy of the system plus the work done by or on the system. Okay. So, we talked about endothermic processes, energy added to the system, where Q is positive. Now, we actually have work done on the system, and I know the word done is bolded, but to me, what needs to be bolded is on. Work done on the system. You're beating on the system. Okay. That is actually that's a positive W. If you have an endothermic, if your system is actually receiving thermal energy, and if work is done on the system, okay, then your internal energy of your system is going to increase. By golly, you've got two positive terms. No doubt about it. Your delta U will be positive. So, let's see. Can't remember how my builds are. Okay, Q is positive. Now, if Q is negative, that's an exothermic sort of situation in which actually your internal energy of your system will decrease. Here we have work done on the system, and here we have work done by the system. Example I looked at a minute ago, this is work done on the system. I would emphasize the word on. And this over here, and you can all see this arrow going outward, this is actually work done by the system. It's done by the system on the surroundings. And if it's work done by the system, this makes sense. It's actually going to be, the W term will be negative. So exothermic, work done by the system, we have negative terms. Okay, endothermic and work done, so endothermic, work done on the system, we have positive terms. Whew, all right then. So we've used Q is change in thermal energy. And actually I'm going to kind of take it up a notch and introduce a new variable, a new concept, enthalpy. Enthalpy. And I hear myself emphasizing because some of you are familiar with the term entropy, which is an awesome concept. And they are not the same thing. Enthalpy, entropy. I wish somebody would have come up with different words. So we're talking about enthalpy. The variable for enthalpy is the capital H. And actually, when we get the ball rolling, I'll just tell you the nuts and bolts of this, and I'll try to explain why. The Q, the change in thermal energy, we can, as long as there's no change in pressure, we can just substitute H for that. Not just any H, but it's change in thermal energy, so it's change in enthalpy. So it's delta H, okay? When we get going here, basically, as long as there's no change in pressure, your Q and your delta H of the process are the same. Okay, bottom line. I looked it up before I came here because I'm like, is there any better way to define this? Oh, no, that's about it. Okay. So again, like how much thermal energy an object has, it's really hard to get a snapshot, but we can look at the change in thermal energy pretty well. Thus, we can look at the change in enthalpy pretty well. So like I said, that Q, change in thermal energy, is equal to the change in enthalpy. Enthalpy is the measure of the thermal energy an object has. So delta H is the measure of the change in enthalpy. So when we work problems, we're going to kind of count on that. We're also going to count on this idea. Later on, okay, we're actually going to have enthalpy values, initial and final. So anytime you see delta, like delta T is the final temperature minus the initial temperature. Delta H is the final enthalpy minus the initial enthalpy. Okay? So there you go. Enthalpy must be our first of several what we call state functions. When I say state function, it's a characteristic. It's an important, I say concept. Okay, state function. What that means is if I were going to let time be along my x-axis, okay, and I'm going to make some, we'll call this how much energy. Specifically, it's the energy associated with enthalpy. And I could have an initial enthalpy here. So I'll make that H sub I. Okay. And over here, I'm going to make an increase in enthalpy. Over here, I'm going to have, this is my final enthalpy. It's kind of an energy diagram. What a state function means, sometimes state function is called path independent. That's the way I think of it. State function, path independent. So I'm going to draw two scenarios. Okay, over time, I'm going to say the enthalpy of the system went up here, and then it went down here, and then it went there, and it kind of went like that. Okay? There's my blue line, my blue scenario. There's my blue path. And here's my other path. I'm going to say it started here. Here's my green. And it went down, and it stayed down, and then it went up and like that. So I have a blue path and a green path. Bottom line with a state function like this, I told you delta H is equal to final minus initial. I don't care how you got there. It's independent of path. It's kind of like your bank account, you know? If you go in the red, as long as you end up in the black, that's okay. Okay. So the opposite of a state function is something that does depend upon the path, and that's a path-dependent function. All right. So here we go. There's our internal energy, actually change in our internal energy again. And now instead of the Q term, as long as it's at constant pressure, which I kind of grapple a little bit with what constant pressure means. But like for instance, when you did your copper experiment, you guys didn't like pressurize your reaction vessel. Okay, you basically let it be at whatever atmospheric pressure was. That's constant pressure. Okay. So as long as that's the case, then we can substitute, instead of Q, we can go with change in enthalpy. The W term is still the work done on the system or by the system. So we have some absolute values here. Of course, you know absolute values means basically makes it positive. That's the way I think of it. Okay. So if the work term, let's just say if the work term, regardless of it being positive or negative, and we run into this in a few places in chemistry too. If you ever see this right here, of course you're familiar with that means less than. If you piggyback two less thans, it means a lot less than. That's it. So if the work term is a lot less than the enthalpy term, the delta H, then basically we say that your work term is negligible, so your work term goes to 0. We do that a lot. If no work is done, or if it's pretty small. In that case, we can rewrite that relationship. The change in energy, internal energy of the system is just equal to the change in enthalpy of the system. That's sounds like it's cheating to me. And then I just have one example, and I think this is a little lame, but maybe it's just me. Okay, so you guys know that like if in physics we talk about if it takes work to lift an object against the force of gravity. So it has a certain amount of actually potential or stored energy here, and it has more potential energy here. Okay, so I'm performing work. And so the way this goes is basically this scenario is performing work on the book. Okay, if you read, it's like, well, what is this scenario? Well, one of the things is, you know, and we're coming up against, this is actually very timely. I'm hoping to grab some dry ice because tomorrow we've got some high school students coming in, a few high school students, and some of them are going to end up down in the chem lab. So I like the whole dry ice thing, okay, where they have this kind of foaming out, okay. But if you take dry ice, it actually will, all it is solid carbon dioxide. And if you allow it into normal, if you take it out of your cooler, it's going to sublime. It's going to go from a solid to a gas. Skip the liquid state, okay? That, by the way, is a very endothermic process. We know it's endothermic, requires energy, because, by golly, you cannot use your hand. If you use your hand, it's going to do that at the expense of the heat, of your own heat, okay? But anyway, so it's a very endothermic process. In the meantime, it basically, as it creates a gas, okay, you're seeing that happen in that Ziploc bag there, that sealed Ziploc bag. So basically, the bag goes from being flat to being, and in doing so, it performs work on the book. I just think this is a stretch, okay, but I suppose. So this is an example where actually the work term, and I was thinking about this at my office, and you guys have some homework where you're going to have to wrestle with this. Okay, if this bag is my system, okay, does this make sense? Work isn't being done on it, but it is doing work, okay? So basically we have this work going out, and we said that would be what? Negative. Okay, so your work term is going to be actually less than 0 here. Endothermic, we said the Q, or the delta H term, Q and delta H are synonymous here. So Q term would be what? Positive, and so would the delta H term would be positive. So this idea here, delta H is positive, so it's Q. Okay, bottom line. Okay. So let's see what your homework looks like. So these will also be due on Fabulous Friday. We'll take a look at these. They look like this. Okay. So yeah, these are just intended to get you thinking about the change in energy of the system being 2 terms. The change in thermal energy, or Q, or delta H, same diff, and the change in, or work done on, or work done by the system. I can't remember what my hints are. I think my hints are pretty in-depth. I think they basically spell it out. Okay, so for A, sometimes it's hard to take like the words and convert them into what's going on, but if you read it a few times, the word absorbs by the system means it's endothermic. So I went ahead and told you that means it's positive. So you would put a plus 58 joules for that. And then I went ahead and it says that actually your system is going to do work. This is kind of like we said, we saw kind of the lifting the book. If it does work, then your W term is going to be negative. Okay, so that's how that goes. I think I did them for, did I do them for all of them? Okay, so those hints are there if you wanted. Okay, so I kind of walked you through. Be careful for C, it's a pain in the batui. Don't blame me, that's kind of chemistry sometimes. But notice we have units of calories and kilojoules. So you're going to either have to convert your kilojoules to calories or your calories to kilojoules before you can work it. But other than that, they're just addition problems. And then the next one I think is kind of similar, and I gave hints for those. I guess I would say 56 is a little different in that it's asking you for the change in, what is the change in internal energy of a system if the surroundings, oh, in this case, it gives you what the surroundings is doing. So I will tell you, it is different. So like for the first one, for A, it says that the surroundings is transferring 235 joules of heat. So it's actually transferring it in. It is endothermic, yep, positive Q. And that the surroundings is doing 128 joules of work, so it's doing it on the system. So that's why it's a positive work term. So those will be out there if you want them. Okay? Sweet. So yeah, we have a session in the library, or we're all just tired of chemistry, everybody goes home.